All right. So today we're going to be looking at section 7. And this is probably going to take this section will probably take more than one day. At least that seems to have been the pattern so far. So when we say function operations, there's kind of 4 basic function operations. And these are the same 4 basic operations that there are for arithmetic. So we're talking about addition, subtraction, multiplication, division. And if I look at sum of 2 functions, so if I look at f plus g of x, this is really easy to compute, and I think that all of us would guess immediately that the way to evaluate the sum of 2 functions is to just add the individual functions. Similar with subtraction. To do the difference of 2 functions, we'll just take the difference of the 2 individuals. For product, same. F times g of x is the same thing as f of x times g of x. And for a quotient, f divided by g of x is the same thing as f of x divided by g of x. With the one little caveat that g of x has to be non-zero. Why do we need that non-zero condition for the quotient? Yeah, we can't divide by 0. So we have to make sure that the denominator is never 0. In this case, g of x is our denominator. So we have that little extra criteria there. So none of these things should come as much of a surprise. This is, I think, intuitively what we would hope to have happen. But just as a nice little piece of review, let's look at a specific example. So let's say f of x is the function 2x minus 3. And g of x is the function the square root of x plus 2. And then let's compute some of these sum difference product quotient. So if I want to compute f plus g of x, we just discussed above that we can do that by adding the individual functions. So I can just do f of x plus g of x. F of x is just the expression 3, and g of x is the expression the square root of x plus 2. And now all I'm left to do is to really simplify or combine like terms here. Is there anything I can do? No, this is as good as it gets. I'm done. That was shockingly easy, right? Everybody's okay with that one? So next, let's do a difference one. So let's say we want to do g minus f of x. Well, according to our rule above, I can compute that by just taking f of x minus g of x. I'm sorry, g of x minus f of x. So I'll make my substitution then, just like we did before. So g of x is the square root of x minus 2. I'll write my subtraction symbol. And then f of x is 2x minus 3. Is this correct? What's wrong with this? Maya? Yeah, so the negative sign applies to f of x, so it applies to the entire expression. So I should have a parenthesis around that 2x minus 3, which means that I would need to make sure I distribute that negative sign through. So my actual answer, as Maya said, is square root of x plus 2 minus 2x plus 3. Very good. Everybody okay with that? And again, easy thing to forget. Part of the reason why we're bothering to do examples of these things that are not computationally terribly difficult gives us an opportunity to review these things that are just like common oopsie-doos that students over the summer will forget. They're like, oh yeah, got to do that. But no big deal. Okay, next one we are going to do is g times g of x. So what I can do is just do g of x times g of x. And then if I substitute in, g of x is the square root of x plus 2. So I'm just left with the square root of x plus 2 times square root of x plus 2. Can I simplify this expression? Yeah. What can I do here? Well, what's x times x? X squared. So if I have the square root of x plus 2 times the square root of x plus 2, I'd have the square root of x plus 2 squared, right? Now what can I do? Yeah, I can cancel the square root and the squared, and I'm left with just x plus 2. Everybody okay with that one? Okay. So the last one, let's look at a quotient. So let's do f divided by g of x. So again, I'll just rewrite this as the quotient of the individual function. So I'll do f of x divided by g of x. And I'll substitute in the variable expressions for each of those, f of x and g of x. So I'm left with 2x minus 3 over square root of x plus 2. Can I do anything with this? What would you want to do? Okay, so Caden suggests that we can rationalize the denominator by multiplying the top and bottom by square root of x plus 2. And that's correct. We can do that, and it's perfectly fine to do that. And in a lot of cases, that's preferable. For this problem, I would say that it's more simple the way it's written. In general, the convention of not having square roots in the denominator is just a convention. So it's like something we agreed to kind of do, like reduce fractions is something that, like, it's not wrong to have an unreduced fraction. It's not like you're expressing a different quantity. It's just a convention. We've decided that we should express answers as reduced fractions. The same idea here goes for these rationalizing of denominators. In general, for me, if it's a variable expression like this, unless I specifically ask you to do it, I don't think it's necessary to rationalize a denominator here. If you did it, I certainly wouldn't mark it wrong, because it's still the correct answer. But if you didn't do it, I wouldn't mark it wrong either. Now, if you have something that's numeric, I would expect you to rationalize the denominator there. So if you had 2 over the square root of 3, I would expect us to rationalize that denominator. If we have 2x minus 3 over the square root of x plus 2, with the x's in there, I'm not really as interested in rationalizing that denominator. So that's kind of where I live. If that changes in my expectation, I'll be very clear to you of kind of the way I would expect that answer formatted. But it kind of in general, there's usually, with a variable expression, you probably don't want to rationalize your denominator unless you know it's actually going to make it simpler. In this case, it doesn't really help a lot. Like, you don't get to cancel anything out. It just kind of makes the problem a little bit messier and takes some more time. I think that this answer, the way it's written, is perfectly fine. Of course, not wrong if you did do it, to be clear. So excellent that you guys remembered that was something to do. That's what I was hoping someone would say, because it allows us to kind of have this discussion about when to rationalize the denominator and when not to. So very good. So there's a fifth operation for functions that doesn't really have a natural corollary to arithmetic. So adding, subtracting, multiplying, dividing, those are all things that we're comfortable with from arithmetic. There's a fifth operation of functions that you've talked about before that doesn't have a natural corollary to arithmetic. Does anybody remember what that fifth operation is called? It starts with a C. We talked about it last year in the first semester. C, O, M, composition, I heard somebody say. That's what I'm looking for. Somebody said that, didn't they? That was you? Way to take credit for someone else's work. I appreciate that. What composition is saying, so the symbol we use for composition of two functions is like that small open circle. It's like the multiplication symbol, but it's not filled in. And the way we perform composition, so f compose g of x is f of x, or I'm sorry, f of g of x. Yeah, good. So you were thinking of this, which is excellent. Yeah, so the name of this is called composition. That's what this operation is, where we plug one function into another. Let's do some examples to remind us kind of the ins and outs of this. So let's suppose our f of x is 2x squared minus 3x. And our g of x is negative 3x plus 4. So we'll do a couple of examples here. So let's start by doing f compose g of x. So the first thing I'm going to do is I'm just going to rewrite this composition using the definition of composition that I gave before. So I'm going to rewrite that as f of g of x. And now I'm going to make a substitution. I'm going to substitute in place of g of x the numeric quantity that it's equal to, which is negative 3x plus 4. Now when we have function notation like this, what this tells us to do is to take whatever's inside those parentheses and plug that in for the x's in our variable expression. So the way I like to do this is I start by rewriting my function or my expression for f of x. But wherever there was an x, I'm going to put a set of parentheses. So notice that what I've done is I recopied exactly my variable expression for f of x, and I just replaced the x's with parentheses. And then what I'm going to do is inside those parentheses, I'm going to write that expression for g of x. So I'm literally just plugging one function into the other. that look familiar, I hope? We remember kind of doing this last year. Maybe, hopefully. It was first semester, so it was a long time ago. I think we did a little bit in second semester, though, too. Yeah, because we talked about inverses in second semester. The last thing I'd left to do here is then to simplify. Is there any simplifying I can do here? Definitely is, right? There's a lot of stuff I can do here, in fact. They're on the roof. You can see the shaking. That's weird. All right. So what's the first thing I should do for the simplifying here? What's the first thing I need to take care of? The exponent. Very good. So if I follow the order of operations, the first thing I would need to take care of is that exponent. What do I need to do that? Like, how do I take care of that exponent? I have to FOIL. I don't distribute exponents. In fact, you never distribute exponents. In fact, the only things that we know that distribute are multiplication, division, and that summation notation from the end of last year in Algebra 3-4. The only three things that you've seen so far that distribute. So we need to FOIL here. This is going to be the only time this year that I'm going to write out a FOIL problem. All the rest of them I'm going to do in my head when we do these notes, but I figure the still kind of reviewing, so I can write this out. So I have negative 3x times negative 3x is negative 9x. 4 times negative 3x is negative 12x. And negative 3x times 4 is also negative 12x. I put them together, I have negative 24x. And then 4 times 4 is 16. Everybody okay to there? Okay. What should I do next? Distribute, yeah. So distribute here with the 2, and then here again with the negative 3. And now once I've distributed, I can combine my like terms. That should be plus 9x. Sweet googly moogly, and that should be a minus 12. My apologies. We all make mistakes. I just made one there. Should I factor this? No. Right? This is fine the way it is. If you factored it, is it wrong? No. It's just not necessary. More often than not, when we say to simplify something, you want it written, as a polynomial. You want to do all the multiplication or whatever. Okay. Let's do another. That was a particularly lengthy one, because we had that foiling involved. I do not. Would you need to, you want to run the bathroom? Yes, you may. Of course. All right. If I'm doing G-compose f of x, I'll start by applying the definition, substituting in for my expression for f of x, and then I'm going to rewrite G but in place of x's, I'm going to write a set of parentheses. And then inside that set of parentheses, I'm going to write that expression for f. And then all I'm left to do is simplify. Here the simplifying is much easier because all I need to do is distribute. And I'm done. What can you say about composition by looking at these two examples here? What can I say about the operation of composition by looking at these two examples? Well, you should notice that F compose G is not the same as G compose F, right? We have a name for when the operation works the same in both orders. Do you remember what that name is? Starts with a C. You said it before when we were talking about we're trying to guess composition. Commutative. So we know that composition is not commutative, right? Because the order in which you do it matters. F of x, or F compose G, is not necessarily going to equal G compose F. Now, because it's not commutative, does it mean it will never be true that F of x, or F compose G, equals G compose F? No, that could still happen. It just won't always happen. Everybody okay with that idea? All right, one last example just for kicks. We'll do this pain in the neck. So, just like before, I'll start by rewriting this composition using the definition of composition. And then in place of f of x, I'm going to variable expression for f of x. And then I'm going to write the variable expression for f of x. But everywhere there's an x, I'm going to replace that with a parenthesis. And then inside of those parentheses, I'm going to put the variable expression for f of x. So I'm literally plugging one function into itself. Now I just need to simplify. The first thing I should do to simplify is to take care of that exponent. To take care of that exponent, I need to FOIL. This foiling that I'm going to do here, I'm just going to write down because I'm going to do it in my head. I warned you guys that this was going to be the only time I write out a FOIL. It was earlier. You're not going to trick me into doing it now. But it should be not too bad to do these in your head. The formula that you can use to kind of do that in your head is just the binomial expansion for a plus b squared. So a squared is here. 2 times a times b is there. And then b squared is there. So it's pretty easy to do that in your head still. Of course, you could write it out. There's no penalty in doing that. I probably will never write out another FOIL in this course. And then we just distribute. Whoop, whoop, whoop. Whoop, whoop, whoop. Why did I write squared there? How come nobody was yet hollering at me that that's supposed to be a 3? Thank you. I appreciate you paying attention. Okay. And then if I finish up combining like terms, I'm left with this as my final answer. Do I need to factor this? No. It's simplified the way it is. If you did factor it, is it wrong? No. It's just unnecessary work. And in a time test setting, probably best not to spend your test time doing unnecessary work, right? Good. Everybody kind of remember doing composition now? Feel pretty okay with it? It's not too terribly bad. Really, the worst part usually ends up the simplifying you have to do after the composition is usually the irritating part. It's like, oh my god, all the simplifying to do. Oh, I got to FOIL this thing out. I know. Life is hard. Yes. Yep. Thank you, Ben. Paying attention, I like it. I'm making all these mistakes on purpose so that you have to pay more attention, right? Everybody knows that. The classic math teacher comment. So, we bothered to define this operation of composition because we're going to use it as part of another definition. Let's use composition notation. So if f and g are functions, we can say that g is the inverse function of f, provided that f compose g of x equals g compose f of x, which also in turn gives us x. So I have to show that both compositions give me x. So what are we really saying there? What that's really saying is that if I apply an inverse and then the function, basically the inverse undoes whatever the function did. So let's look at that in maybe a more conceptual way. So let's imagine we have a function f of x, and I'll write this function as a mapping diagram. So here's my domain. Here's my range. And we'll call this function f. What this mapping diagram is saying is that f of 1 gives me 4, f of 2 gives me 6, and f of 3 gives me 5. Can everybody kind of see that? Okay. So we had this definition of an inverse here where we use composition really to kind of define that inverse. And while that's a really nice definition if I want to try to prove something, it's not very intuitive for us. Does anyone remember from last year kind of the intuitive way we described finding an inverse or what an inverse is? Okay. okay. That's okay. So when we talked last year about inverses, we talked about needing to swap the x and y coordinates, and the resulting relation was our inverse. So in our case, if we look at this function f, if I swap the x's and y's, 4, 5, and 6 would be the domain, and 1, 2, and 3 would be the range. So 4 would pair to 1, 5 would pair to 3, 6 would pair with 2, and the name we gave for an inverse, we use that f to the negative 1 notation. That was the notation we used for inverse. Keep in mind that that f to the negative 1 does not mean 1 over x or 1 over f. It's not an exponent. Just as a little aside here. F of negative x is the inverse. F of x to the negative 1, that's the reciprocal. So where you put that negative 1 means two different things. When it's attached to just the f, we're talking about an inverse. When it's wrapped around the entire f of x, that's when we're talking about the reciprocal. Everybody okay with that idea? That's just a little aside there. So if I write out this function using function notation, I would say that f inverse of 4 is 1, f inverse of 5 is 3, and f inverse of 6 is 2. Everybody agree with that? So if I look at f of f inverse of 4, what would I say here? Well, I know that f inverse of 4 is equal to 1, right? So I can replace f inverse of 4 with 1. And then I know f of 1 is 4. Everybody see that? Similarly, if I did f inverse of f of 1, I can say that that is f inverse of 4, and f inverse of 4 gives me 1. So this is basically like when we said that f of g of x has to equal x in our definition. So like x is the 1. So that's what why that definition using composition is really saying the same thing as our intuitive definition that we talked about last year, where we want to just swap those x's and y's. Does everybody feel okay with that? I know there's a lot of notation there, but hopefully that made sense a little bit more when we plug some numbers in and just show numerically why that definition is kind of the same thing, or why those two descriptions are really the same thing. Does everybody feel okay with that idea? All right. Good. Let's look at another situation. This time, instead of our function f of x being described using a mapping diagram, I'll describe my function f of x with a set of ordered pairs. In this case, if I were to write down the inverse, what would I say the inverse is? Good. 4, negative 2, 6, negative 1, 8.3, 8.5. Excellent. So all we did was we switched the x and y coordinates, right? Does anybody notice anything odd about F inverse in this situation? There is something unfortunate. What's that, Caden? It's not a function, right? So notice that we have repeating x coordinates, which would tell us that this is not a function. In our previous example, was our inverse a function? We scroll back up here and look. That's definitely a function, right? So we've seen that sometimes when we find an inverse, that inverse is a function. And we found that other times when we find an inverse, that inverse is not a function. What we'd like to be able to do is come up with a criteria that we can use to check before we find that inverse whether or not that inverse would be a function or not. So to do that, I need to define some vocabulary. So that's what we'll do next. So this first definition says a function is considered onto or surjective. Those two terms get used kind of interchangeably. It's probably a 50-50 split in my experience of which term would be used. So they're both quite common. If every element in the range is mapped to by some element in... That wouldn't have made any sense. Try the domain. So basically what this is saying is that you don't have any unused values in your range. So everybody's okay with that idea? Next definition. So this definition says a function is considered one-to-one, or injective is the other term that we have for that. Again, those two terms are probably about equally commonly used. If every element in the domain maps uniquely to distinct elements in the range. What this is basically saying is that no y coordinates get repeated. You can't use any y coordinate more than one time. Okay. And then one last definition. So we say a function that is both onto and one-to-one is called bijective. Everybody okay with that idea? All right, so let's do just a little bit of practice identifying whether something is onto, one-to-one, bijective, neither. Okay? So we'll start with mapping diagrams, and then after we've done some mapping diagrams, we'll do some graphs. Everybody's okay with that plan? All right. And again, the point here is just to get comfortable looking at the function and identifying whether it's going to be, which of these attributes it has. And then probably we'll even write the inverses so you can kind of get a feel for like why this is why this property might be related to whether an inverse is a function or not. So we saw this function just a moment ago, right? Is this onto? Is everything in the range used? Yes. So this is onto. Is it one-to-one? Yes, none of the y coordinates are used more than once. So we would say that this is then bijective. Right? We noticed that when we found the inverse for this, this is a function. In addition, what kind of function is it? This is also bijective, right? If you notice, it's also one-to-one and onto. Okay? Let's do another example here. And I apologize for picking the most space using notation to look at this at, but it's really the kind of the easiest one to get a feel for the properties, as it's so visual. Call this guy G. So G is definitely a function, right? Okay. Is it one-to-one? I'm sorry, is it onto? That's what I wrote down first. Is it onto? I see people shaking their heads no. That no is the correct answer. What's the issue? Yeah, that 7 isn't used by anything. Like there's no x value that's going to give you a 7. Okay. Is it one-to-one? Yeah, none of those y values are used more than once. So it is one-to-one. So let's look at what its inverse would look like then. is this a function? What do you think? It's not. The issue is not everything in the domain is used. So the point of this, what we want to observe is, if f is not onto, when I find f inverse, I will, by like definition of onto, have some x coordinate that doesn't go anywhere, which causes that inverse to no longer be a function. Everybody's okay with that idea? Okay. Let's do another example. H, I think, is the next letter in the alphabet. So let's first start. Is this function onto? Yes, right? All the y's get used. Is it one-to-one? No. The issue being that 4 is used more than once. Everybody feel okay with that? Okay. Let's find the inverse then. Is this a function? No. What's the issue? Great, because the x-coordinate of 4 is used twice. So we see that if a function is not one-to-one, when I find its inverse, I'm going to have at least one x-coordinate that goes to 2 places. So in order for me to be guaranteed that when I find my inverse it's a function, what do I need to have? I need to have one-to-one, and I need to have onto. I need that function to be bijective to guarantee that its inverse will also be a function. I guess we'll stop here. We'll talk, remind me when we come back and meet again that we want to look at some graphs also for this.